sir. Again, welcome you on this
Thank
platform.
you.
And now platform is all yours. Over to you, sir.
Thank you, Dr. Mao.
आप बोलते ना
Yeah.
हमें इतना नहीं 1000-2000 के पीछे हम कभी भी अपने
Yeah. Hello, all. So, welcome again to in continuation of the previous session. We are learning the classification of states, and then how do we classify them as a recurrent state, transient state, or absorbing state. And we saw a numerical example, and we'll continue with that example now again for more further understanding of the classification of the states. Let me share my screen. Yeah. So this is how we understand the same picture, whatever I drawn here, it is there in the slide. That means the class, if you see that 1, 2, 3 forms a class. That means 1, 2, the states 1, 2, 3. We are not saying they are closed or not closed, but just saying they all communicate with each other. 1 and 2 are communicating, 2 and 3 are communicating. That's why 1 and 3 also communicate. 1 and 3, the states 1 and 3 also communicating. That's why we call 1, 2, 3 is a class. Similarly, 4 is a class. So 4 is a class. 4 itself communicates. It doesn't communicate with others. 3 is communicating with 4. 3 is a transition. There is a transition from 3 to 4. That's what we draw here, 3 to 4. The same thing in another way I draw, 3 to 4. But 4 is, there is no transition from 4 to 3. So as we saw that previously, that 1 to 2, 2 to 3, that's why the transitive law says 1 and 3 are communicating to each other. 2 to 3 there is a transition, but 3 to 2 there is no transition. But 3 to 1 there is a transition, 1 to 2. So that means 3 and 2 are communicating. Whereas 3 to 4, there is a random variable can reach from 3 to 4. But 4 to 5, there is no mechanism to, 4 to 3, there is no mechanism to, there is no transition probability to reach 3 from 4. So 4 is not communicating with 5. If the random variable leaves 4, and from 5 it cannot come back to 4, either directly or indirectly.
So, sir, I have a query here.
Yes.
So in this graphical representation of the problem, because now it has been modeled as a graph, so are we trying to find the strongly connected component? Because I mean, in this explanation, I have this feeling that as if we are trying to find the strongly connected components and indicating one component as a class.
Correct. I mean, the word, we don't use the strongly or weakly here. What we are saying is they are communicating or not communicating. When two states are communicating, or according to our definition, two states are communicating means this is a double arrow.
Yes.
Two-sided arrow that I is communicating with J is with I, need not be directly. It could be indirectly also.
Right, sir. So basically, we are trying to find the subset of the edges in such a way so that if we can traverse from I to J, then we should be able to traverse from J to I as well.
Correct, J to I. Then only we say they are communicating to each other. They're communicating. Only one way transition, we don't say communication.
Right, sir. Right, sir. Okay, sir.
One way we don't say. So two-way communication. And our aim is, when we did the purpose of definition of closed set is the word. Intuitionally already it is clear to you. You asked a good question. We are already clear to all of you that we are trying to reduce the bigger space into a smaller space which is closed. That's the aim. The reason for that is, as I mentioned, the bigger the state space, Sometimes it is a classification becomes more complex, and then we may have to unnecessarily incorporate a lot of states which are not having any communication with the other states.
Right.
We want to reduce it. That's why you see that here 4 itself is a class, and 5, 6 is a class and is closed. Rest 2 are not closed, but 5, 6 is a closed. 5, 6 is a class and it is closed. Why it is closed? Because why it is closed here, 5 to 6, the communication from 5 to other states is not happening other than 6.
Yes.
Similarly, 6 outside from 6, the communication is not happening beyond 5.
And sir, moreover, it is forming a partition 1, 2, 3, and then 4, and then 5, 6.
Correct. Partition. We are reducing the bigger space into smaller spaces, smaller state spaces.
Right.
Correct. Partitioning. Correct. You are doing using right word. So that's the purpose. Next is automatically we are defining irreducible. A set C is irreducible because a closed set we cannot. If a set is closed, we cannot make them into further smaller sets. A closed set means in this, not in the real analysis concept, the closed set in terms of a stochastic process state spaces. A closed set we cannot further reduce into further smaller sets. Once it is closed, that means each and every state is communicating with other states, either directly, indirectly. We cannot reduce it further. So a closed set is irreducible if I and j, for every I comma j, if a closed set C is irreducible if I comma j communicate each other for every I comma j in C. We'll see for bigger examples also. But in this case, we have only 2 I comma 6. They communicate with each other. That is irreducible. We cannot make 5 itself as a single class. We cannot make it because 5 and 6 are communicating and both are recurrent. So we cannot make any. That means they are irreducible. That 5 comma 6 are irreducible. Similarly, the 2 events TI, recurrent class. So I want to skip this. Already we discussed this. Let me skip this. So already we discussed several times the meaning of that. The same thing we discussed also, that thing also I discussed. I just put it in case we have any questions. So as we also, the same thing we discussed, a transient state can be visited at most finite number of times, no matter where the change starts. Similarly, that's why here you see that in this example, the previous example, 1, 2, 3, they're transient, but they are not recurrent. The same thing written here. 1, 2, 3 can be revisited at most finite number of times. But we cannot write that the transient always forever it will reach. We are not sure that it will come back infinitely many times. Once it leaves 3, similarly in this example. So in this example, if you see leaves 3, as long as the state is as long as the random variable come back to 1, it can come to 3 and 4. But once it leaves 3, there is no mechanism to come back to 3. The random variable cannot come back to 3. Hence, the chain is broken, and 1, 2. That's why 1, 2, 3 are the class. 1, 2, 3 are transient class. 1, 2 transient class. 4 also transient. 5, 6 is closed, and they are recurrent. That's what it means. That is what. So Fij, if the state is J, Fij, Fjj equal to 1 means it is sure that leaving J state will come back to J. So this I leave as a homework. We all have to think on that. If j is recurrent, then expectation of nj. Nj means again number of times starting from I reaching j is 0 if Fij is 0. If Fij 0 means I to j starting from I never reaches j. There is no minimum value, then is 0. Fij greater than 0, it's infinity and expectation value is infinite. So in particular, if j is recurrent, just think on that, just a one-line answers only. Just think on that as a after course homework. So again, coming back to the just on same thing, since we learned now the recurrence and transient classes, recurrent transient classes, we'll see how that is applied on the random walk on integer lattice again. So you take the integer number 1, 2, 3, and -1, -2, and so on. So probability of transition from higher state from -2 to -1, -1 to 0, their probability P, and coming back to the lower state, returning to lower state is transition to lower state is 1 minus P. So P 1 minus P. So this is a transition. It never stays in any state. It keep on with the probability 1 minus P. It keep on going. So that's why the random walk example or gambler's ruin examples, the classical examples for us to come back to the definitions and understand how these definitions are applied. The same thing, this thing in a transition matrix. The previous graph in a transition matrix, it look like that. So you can draw yourself. I'm going to send the slides anyway. So please draw yourself after the coursework is over. This is interesting again, and to understand using the Bernoulli principle, how do we understand the transition, the random walk, construction of the random walk? So the same problem, let us understand that. This is again a theoretical example. I to j in that for the previous example, nth time step, Pij in nth time step can be written as, because if you see that in the previous slide, take 0 to 1 in one step, it can reach, isn't it? And 0 to 2, it can reach in 2 steps. Similarly, 0 to 0, it cannot reach in one step. It has to reach in 2 steps. One step to go, come back. Or if you go this side, come back. 0 to -1, -1 to 0. So it takes 2 steps to come back to the same state. 2, similarly 2, and then reaching here. All of you carefully follow here. 0 to -1, -1 to 2. 0 to -1, 1 step. -1 to -2, 2 steps. -2 to -1, 3 step, third step. -1 to 0, fourth step. 4 steps to come back to 0. So either it can come back in 2 steps, it can come back in 4 steps. It cannot come back in 3 steps. It cannot come back in 5 steps. Similarly, you take a state 1, 1 to 2, 2 to 1, 2 steps. 1 to 0, 0 to 1, 2 steps. Or 1 to 0, 0 to -1, -1 to 0, 0 to 1, 4 steps. So 2, 4, 6, and so on. Reaching a neighboring state takes odd numbers. See here, 3, it can 1 to 0 in 1 step. Okay, 1 to 0, how many steps? 1 step. Again 0 to 1, 2 steps. Again 1 to 0, how many steps? 3 steps. Minimum time, the minimum time either 1 step, or 3 steps. So, and fifth step, and 7th step, and so on. See here, 1 to 0, 1 step, 0 to -1, 2 steps, and -1 to 0 again, third step, 3 steps. So reaching the neighboring state can be in odd numbers, only in odd numbers, reaching the same state in even number. Okay, that need to be carefully understood. That's what it is. So reaching the n choose u, p to the power of u. P is probability to move to higher state. 1 minus p is the probability to lower state for 0 to less than 2, and so that means I to j, if that is the 0 n plus j minus I. So if n is a state 3, j is 1 and I is 0, 3 plus 1 minus 0. 4 minus 0 is 4. That's an odd number. I mean, it's an even number, so 2n. And if it is a n plus j minus I is even, this is if there is even, it will go to the different state. So come back to the same state in odd number, come back to a different state in even number. That's what it is. U equal to n plus j minus I, n minus u. That's the purpose of the reaching. How do we n choose u? If you expand this, for p, for probability moving forward, 1 minus p is to probability to return back to the moving forward, coming back. P is the probability to move forward, 1 minus p is the probability to backward to the previous state. So probability of transition from state I to state j in n time steps can be expressed in terms of a binomial expansion. U equal to, where u equal n plus j minus I by 2 for upward and n minus u for downward. You can verify that. Yeah. These are all things, as I mentioned, you may understand as I explained, the first timers, but better to practice with pen and paper after each lecture. Then only that it will be more clearer. And when you apply your own, these all analysis, these kind of things for the data. So this is a pattern, this observation of a pattern. Similarly, for a COVID data, you might observe some pattern that becomes a model for the COVID data. This is the model for the PIJN, is a model, binomial model for the random walk on an integer lattice. Similarly, for the data.
Upward and downward means indicates here?
Upward means, going higher state, downward means lower state. Like 1 to 0 is a downward and 1 to 2 is an upward.
Okay, indicated by the arrows.
In the previous slide, you see here, here 1 to 0 is a state, upward, 0 to 1, 1 to 2. Going higher state. Going to lower state is a downward. 1 minus p is a probability to come down. 0 to -1, -1 to -2, downward.
Okay.
So this is a understanding of the gambler's ruin model or random walk on integer lattice. And when this is the research part I'm explaining. So when you have your own data, you have to build your own model for that kind of data, and then argue saying that these are the recurrent classes, these are the transient classes, this is what the data, this is the state space, this is the model, this is how the research expands. Research of a particular area expands by understanding various patterns of the data, various properties. You can come up with a new model of the random walk, different kind of generation on the random walk, as I'm giving the building example or the office example in the first day. So like that, you have to understand the foundations very thoroughly, very, very thoroughly, without any confusion, and then apply those things on your own kind of data which you come across. So this is again statement here. The chain is transient when p not equal to half and it's closed. So you see that here automatically we noted that point. That is closed because p is not equal to half. Automatically, they keep on trying this thing. You are not sure that it will come back. Now you see, if you take only the positive side, z plus positive integers and a union of 0, the singleton, and then that's the state space, then P001, then the chain is not closed because 0 is not communicating other states. So that means here what I meant was, let me draw here itself. 0, 1, 2, and so on. And P00 is 1 is given. Suppose P00 equal to 1. That means P001 means what? Probability that it is a state random variable from state 0 to transition to state 0 is 1. That means as soon as the random variable reaches state 0, it will be there. So from 2 to whenever the probability, there's a probability to P and 1 minus P, probability to come back. Similarly, probability P and so on. So they all communicate, but then 1 to 2, 2 to 3, and so on can happen. But as soon as the random variable reaches state 0, P001. So that means this chain means chain with the states 0, 1, 2, 3, etc. is not closed. The state, if the state is, that this is our state. Suppose this is the state space. So the state space 1, 2, 3, and so on, including 0, is not closed because P00 is equal to 1. So that's how you in your data, the practical applications of that, as we discussed today, and the COVID data, other things. You construct when you build your own, you collect your data from your hospital. You bring all these properties for the data. Of course, partially the first part is to help the hospital management and the patients done. Then the theoretical, all the things of academic interest, one can carry and then see. That becomes a research question. And then what are the new properties you came across? What the transition matrix look like? What is the differential equation? How you formulated? All these things as a research question. These all evolve as a research question. And then the original work comes out from you, all the participants. The original work comes out, and that becomes a inspiration for others. So that's what this theory is not detached to the what the things you are doing practically. All the practicalities what we are doing can be make it more enriching experience when we combine them with the knowledge what we have. So let us take another example. Another example here. There are 5 states out there, and then communication. You see that from the instantly as soon as you see the matrix, you see that here 1 and 2 are communicating with each other, and that is closed, isn't it? 1 and 2 are closed. They're communicating with each other. 3, 4, 5 are communicating with each other. That is closed. So the state space 1, 2, 3, 4, 5. 1, 2 is a closed state space out of the. If I see the state space 1, 2, 3, 4, 5, C is 1, 2. So C1 first closed set. Another closed set is 3, 4, 5. So this is a closed set. This is a closed set. because 3, 4, 5 are communicating with each other. 3 to 3, 3 to 4, 3 to 5. So, and then this is also stochastic matrix. See, the same thing. 1, 2 is communicating. 3, 4, 5 is communicating. So not irreducible. Not irreducible means irreducible. So that can be, you can bring down. So 1, 2, 3, 4, 5, you can broken down. It can be into 1, 2, one communicating class. 3, 4, 5 is a communicating class. So this is the outcome. This is this kind of numerical outcomes. You have to come up with your own data. That's the research. That's how the research original research. So you come up with your own, and then the model also may be different. You when you see the data, what is the better model? The binomial example just now we saw. Similarly, what pattern you can observe from the data what you collected from the hospital. That provides you an intuition to develop your own model, mathematical model, stochastic model, and then predict the probabilities. Let us take another example. See 1, 2, 3, 4, 4 are there. See here 1, 2 are communicating with each other. 1, 2 communicate 1 to 2 transition with the probability 2/3, 2 to 1. And 3, 4 are not communicating with 1 and 2. So that is how we try to the classification of states. So some of the slides which I skipped for you to as a homework, please take them also seriously after the coursework. And anyway, all the slides will be with you. And yesterday's the mathematical models that what I explained for HIV, that also those also you must have already with you. So these are all post coursework assignments. Same thing, that we just saw 1, 2. So here you see that probability here 3 to 3 is 5/6 probability to stay back in the 3. 5/6 probability leaving 3 to 4 is 1/6. But once the random variable reaches state 4, it remains there. That's why 3 is a communicating class, 4 is a communicating class. 3 to transition 4 can happen, but 4 to 3 cannot happen. So 1, 2, 3, 4 is reduced into 1, 2, 3, 3 and 4. So the same thing, the chance of staying. The probability 3 in that matrix, you see, the chance of staying in the state 2 forever. That means the probability 1/3 there, 1/3. So 1/3 to the power of n, that means a p square, if you make all that higher powers, as we discussed initially, higher powers also you can make. Yeah, because it is online, you have to carefully work out. If it is in person, I would have made you in the class itself to compute all these things. But since it is online, you have to do it after the course, or just to have a maximum utility of the course. Although we are discussing very thoroughly in the class here, but some practice also very much needed. If it is in-person class, the tutorials are ideally to make you work out in the class. But here, because of the situation, you have to put some extra effort to after the course. I know you are all busy your own. Some of you are faculty members somewhere. Please take out some time to make sure that all these are you are working out yourself. The same thing explained. The higher you take the higher powers, and then in the 1/3 power n means as n goes to infinity. The limit as n goes to infinity. This is 0. Similarly, chance of staying forever in state 1 is 0, thus 1, 2 is recurrent. That previous, as already we discussed. Similarly, 3 and 4 is recurrent because 4 is absorbing, 4 is recurrent, 3 is a transient. See here. 3 once leaves 3, as we discussed, 3 to 4, there is no guarantee that it will come back to 3. So 3 is transient. But 1 and 2 are recurrent. 1 to 2 infinitely many times. It can stay 1 to 3, 1 to 2, 2 to 1, 1 to 2, 2 to 1, keep on happening. So 1 and 2 are recurrent and they are communicating, and 4 is absorbing, so anyway it is recurrent. So since 5, that means F33, since it is you can be another way also theoretically, F33 is less than 1. So F33 means what? Here again, reaching 3 to 3 first time or second time. First time, if first time step it may have come back to 3, second time step it may have come back to 3, third. All the probabilities you need to add. Sum of all that. So let us take that. Let us take that away, some deeper discussion here. What is our definition? F33. According to our definition, F33 is sum of F33 n equal to 1 to infinity. We define for Fij. Now I and j are same. This is same as reaching probability T3 equal to n. T3 equal to n given starting from x0 equal to 3. Isn't it? That the definition, whatever, just Ij, I'm putting that in the. So T3 reaching state 3 n. So T3 means first time. T, what is our definition of T? Ti we defined as minimum. Again, quick recap. Minimum of n such that n greater than or equal to 1 and x0 equal to I, beginning from I. First time reaching the state n, first time reaching the state I in the nth time step, minimum. So F33 means what? Here in this example, F33, leaving 3, the chance can come back to 3 in the first time step. It may come back the same in the data. Yeah, in this example, not the previous example. So 3 to 3, once the random variable leaves the state 3, it will reach only 4. Reach 4 with a probability 1/6. And then 4 to, as soon as it reaches 4, remains at 4. Or the random variable may remain in 3 with probability 5/6. So each time, so if x0 equal to 3, x1 could be 3 or 4. The chance of staying in 3 is 5/6. The chance of leaving 3 and reaching 4 is 1 by 6. So there is some chance there, 5 by 6, to stay at 3. X2, again X2, if it reaches 3, again may stay at 3 or leave for 4. X3, again 3 or 4, starting from 3 I mean. Then X4 is, may suppose it leaves 3 and reaches 4. That's it. There is some chance to leave 3, so it will reach. That's why 5 by 6 power n, that one in F3, so F33, that's why we meant by here F33. F33 is less than 1. No guarantee that F33 equal to 1. Whereas in this case here, F11 means leaving 1, it may go. So if you say F11 equal to 1, that means if X0 equal to, in this case, let me go to the same slide. If X0 equal to 1, X1 equal to either 1 or 2. 1 or 2. X2 equal to, again, if it reaches 1 or 2, if it reaches X2 equal to, second time it is one of that. And suppose it is 2, suppose X2 equal to 2, then X3 again, it may be in 2 or come back to 1. Similarly, X4, maybe if it is 1, it will again come back to either stay at 1 or transition to 2. And these keep on happening infinitely many times. Even if it stays there, fine. If it leaves, again come back another step. There is a possibility to come back for sure. Some other step. That's why 1, 2 are recurrent. Even according to, so that's why F11 equal to 1, F11 equal to 1, comma, F22 also equal to 1. F11 equal to 1 and F22 also equal to 1. Then the periodicity, the name itself suggests that periodicity means what is the frequency to come back in a way, in a simple way, DI, greatest common divisor. If it comes in, each time it will come back in the, third time or sixth time, ninth time. So GCD of that. At sixth time, 24th time, 72nd time, and so on. So GCD of that. What is the frequency to come back? So we say that, that is periodicity at what period? What is the period of coming back? And when that's what the GCD, same definition with N, with the PIAN, reaching, come back. So that's how the probability to come back. And what is the period? If the DI equal to 1, that means, minimum time, the N equal to only 1. You say it's aperiodic, there is no periodicity. Whatever the DI value more than 1, we say that is a period. So Markov chains periodicity of the chain. Each state, what is the period? The DI, within the chain, the entire chain. Each state of the chain can be verified for what is the periodicity of that particular chain. So that actually, this is a snapshot of the classification of the states. As I mentioned, this brings a lot of intuition for you. Now you learn, you please practice yourself with that's important. With the pen and paper, you all have to thoroughly practice them with that. Otherwise, these all look very nice when you listen, like a story, especially in the math. But then when you don't practice it, when you don't verify yourself with the symbols and the notation, all that, it becomes, later after some time you will forget. So please practice yourself, and then even after the coursework, all the slides will be with you. So make sure that you understand each and everything, because we explained everything. Otherwise, you watch the videos available which they are releasing online. So that way, all or everything, each and every concept, you can check with yourself, pen and paper, and then go back to the slide, understand them again, repeat for entire course. So that way, that totality, all the things, and come back to the examples and see the recurrent and transient, how that is happening, how you're defining, and then practically you test it for the real world data. Some more examples, if you see the theoretical example, let us understand some interesting examples. Let us see a transition matrix P. Some matrix, I didn't put any numerical values here. Carefully, let us understand carefully. 0, P12. P12 means, here we have 1, 2, 3, 4. P12. This is a 1, 2, 3, 4. This value P12. Means transition from 1 to 2, 2 to 4, 3 to 1, 3 to 4 2. Now all of you, if the class I would have given this as p square. When you compute p square, means you matrix multiplication. That would be this thing. So all of you, I'll just hold for a minute. Please try to, if you have pen and paper with you, please compute that. Please, if this is p, this is our p square. Just a minute. Oops. Yeah. So p square. Please verify yourself the p square values. So this is the first time reaching, and this is the second time. This is second P1 to 4 in the 2 steps. P1 to 4. P1 4 2 means 2 time steps to reach 4. They got P into P square. First time it reached 2, 1 to 2, and 2 to 4. Second time. So P1 to 4, it reached in 2 time steps. So this is a matrix. P square is given like that. So please verify or just see what happened on the screen. Now, if you see that P11 is in the the next computation, P cube, sorry, P square, and then next if you compute P cube. Again, I'm since I pre-computed, you all can only check post-lecture only. So P11, now we see that here, we note although P11 is 0 first time, P22, P33 at first time steps are 0. But you see that P222, that means second time 2 to 2 could happen here, P22, but initially P22 was 0. Isn't it? P22 is 0. But P22 probability transition from state 2 to state 2 can occur in the second time step. Second time step. So we compute, that's observation. Then again, similarly, if you compute P cube, that is P square into P, and then you again matrix multiplication when you do, you obtain P1, 2, 3. You see that P3, if you all of you observe, P cube again same as, the probability values are different. As other day also someone asked a good question about the values are different, smaller. Yes, probability values could be different, but there is a P13 is P133, P123. The position here, this is a positive value, and see here P12 also positive. So P cube, the values may be different, but it resembles P. isn't it? The locations of the positions here, they're all positive, 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 positive. This is similar to this value. This is P. Not value wise, but location wise. P12. So P square is different different in terms of the position of these values P14, whereas P in the first transition from 1 to 4 can occur in the first step. It is 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1 to 2, 1 to 4 cannot, the probability of transition from 1 to 4 is not possible. But whereas here, P square, it is possible. Similarly, P cube, again, it is not possible. P cube, it is P1 to 2 is possible in third step. So P4, when you compute again, P4 is similar to, again, P square. P cube is similar to P. P for 4 is similar to P square. So again, the same form obtained, isn't it? Same form is obtained. That's why the states 2, 4 are periodic with period 2. That's the purpose of the periodicity. So you also learned the recurrence, transient, and then given a state is recurrent state or not. Now you understood. And given a state absorbing or not. If the state is, the set of states are closed and they're communicating or not communicating, they're reducible, irreducible, and then finally periodicity. That means they all having what is the period. So 2, 4, they each, that means you see that P square, you can verify that P power 5 also will be similar as a homework you can take after the course. P power 5 is similar to P cube, which is equal to P, I mean locations wise, I'm not talking about the numerical values. I hope that is clear. I'm not talking about numerical value of that. So the communication wise that is happening. So P power 4 similar to P square, and so we don't have to compute the higher transient matrices. So the transitions are happening at higher n values are not. That is what we are able to understand. So states 2, 4 are periodic with period 2. Here the GCD we can compute 2, 4 and so on for the higher 2, 2, 4, 6 and so on. So this is the last example for since I'm showing more and more examples. This is just to make you understand the concepts more and more clearer. Because the foundation of the definitions are very that we spend a lot of time on the definitions and then theory, and then we are understanding the numerical examples. So given a matrix P in this form, this is a stochastic matrix we verify. You can see that the sum of each row is 1, 2, 1/3, 2/3, 2/3, 1/3, 5, 6, 1, 6. Almost same as the other matrix, but I just jumbled here and there. So reshuffle the values within the matrix. So yeah, this is in this example. Let us draw this. The transition graph. So if that is 1, 2, 3, 4, 1, 2, 3, 4, the transition graph 1, 2, 3, 4. This is my 4. Okay, so 1 to 1, there is no chance to stay there. 1 to 2, 1 to 3, 2 to 1, 2 to 3. Three to 2. 3 to 4. And 4 to 4. 4 to 4 remaining is 4 to 4 with probability 1. So you say 1 and 2 are communicating with each other.
Sir, 4 to 4 is 0, na?
Sorry, 4 to 2. I'm sorry. Yeah, 4 to 4 is 0. You're right. Thank you. 4 to 2. Now, once a random variable leaves 1, it can go to 3 or it can go to 2. So suppose it goes to 2, random variable in the next step. 2, again come back to 1. If it reaches 3, 3 to 4, 4 to 2, 2 to 1. So 1 is recurrent. Infinitely many times it can come back to 1. 2, it leaves 2 to 1 only, there is a possibility, there is no other way. 2 to 3 also. So 2 to 3, again 3 to 4, 4 to 2. Or 2 to 1, 1 to 3, 3 to 4, 4 to 2. So 2 is also recurrent. 3, let us take 3. 3 to 4, 4 to 2, and so on. 3 to 2, and so on. So 3 is also recurrent. 4 to 2, 2 to 3, 3 to 4. 4 is only one option. It can make. So 1, 2, 3, 4 is this matrix. This is the states S. 1, 2, 3, 4 is not reducible. That means this state space itself is closed. There is no closed subset of that. That's observation, isn't it? One of the observations is that S itself is closed. And this is irreducible. S is the state space, S is irreducible.
Sir, I have a question here.
Yes, please. Please.
Yeah. So, sir, the question is that, what is the implication of having some of the states as recurrent or transient?
Good question. Why do we need to understand? That's what we want to. A recurrent state means it can come back infinitely many times to the same state.
Mm-hmm.
In a real world situation, you want theoretical consequence or real world consequences?
A real world consequence. I mean, how to perceive a recurrent or a transient state? What is the intuition behind? What could be the? In the real world scenario, how to perceive a recurrent or a transient state?
Correct. Because theoretically, we already saw in the random walks how that behavior and recurrent and transient and how that is happening. Already we saw that.
Yes, sir, yes.
State can come back. In terms of the real world, especially the nuclear, the fission, that kind of experiments, various states of the elements, especially the application of this in the, I also saw that some of the articles on the non-medical applications, like the status of the elements, how long, the various properties, electromagnetic inductions, when they do, the state of the certain materials in the space, for example, how long the materials remain in the same properties, how long they hold, or do they change according to temperature. All that, the classification of the various materials they do, and then they try to understand the frequency of coming back to certain things. For example, I given the space rockets, spaceships. Certain materials are used which only trigger expansion of the only under certain temperatures.
Mhm.
Say you take a small piece of matchbox. We can keep certain elements in the match under certain shaped objects within a matchbox. Keep it in a spaceship, in a rocket, and then that rocket, when it reaches certain temperature in the outer sphere, then only this matchbox gets expanded into a certain shape, say an antenna. But antenna can be kept inside the matchbox in a form, it looks like a matchbox only. And then that expands only under certain temperatures. If the temperature is not touched, then it will remain as a matchbox. If it expands, the same matchbox is expanded into an antenna in the beginning itself, it hampers the spaceship travel.
Mhm.
So this is one example where what is the chance of they do experiments on what is the chance that certain elements remain in the same state forever. And also this is one example I gave you. And the other real world situation also, even for the medical sciences, one can also, I'm just thinking as you asked about regarding the COVID, the treatment, in fact, how long a treatment one can, one can give on a patient, radiation therapy or a cancer patients, other things, how long an individual remain there in the same state and also travels to so suppose a COVID patient might acquire some other complications, and again that can come back to the normal situation again after some time. Say after 5 days, a COVID patient after treatment may give it more chest complications. And after 5, 6, 7, 8th day, again come back to a normal situation.
Mhm.
But just for the sake of stochastic process verification, we can't keep a patient for longer period. We can discharge
Yes.
after 10 days. And just because we want to experiment it, we will let us see the 15th day what happened, periodicity of the patient. We don't want to compute that.
Please.
So with this lecture, with this slide, I would like to stop for today's. We went so ahead. We learned so many things. And I'll see tomorrow also. I'll come up with more examples. If possible, I'll try to come with some cardiology examples of the Markov chain in the biostatistical models, and also I'll talk to the Professor Kumar and Professor Redhu and see whether we can include a COVID example, real world COVID example on the mathematical modeling side. But feel free to stop me here and then ask any questions in this lecture or previous couple of days lecture. This is today's 4th day. So any question on the previous days, all these things, just stop me. We have 5 minutes time. So feel free to ask me.
So, sir, can you suggest any small tutorial wherein an end-to-end study is given through the modeling of this Markov chain concept?
Yes, the other study I want to send. Even I try to download that infertility article myself. It is asking me to pay some money to download my own article. I have to see the PDF somewhere. I will share with you all, like the infertility data or the lot of studies you can Google online. Lot of studies are there. You asking the research articles or what is that question, please?
Sir, a tutorial style document which gives an end-to-end study of even of a small problem and using Markov chain.
Okay, so in that case, if the Professor Kumar, you are there, Professor Kumar? Professor Kumar जी
Yes,
आप हैं? तो कल
yes, I'm
क्या
here,
करें?
sir.
कल क्या उनको पूरा 1 घंटा इन क्लास में हमको कंपटीशन वो सब करा देंगे?
In fact, today we have a tutorial. It is going on. Tutorial is going on. We can have today only, if possible. Otherwise, tomorrow we'll be having 5 to 6
टुडे
tests.
मतलब अभी क्या आज है? 1 मिनट, सॉरी, तो आज क्या 9 बजे? अच्छा, अभी 1 more hour is there?
Yeah, it is there.
Oh, I see. Okay, then I can do right away after the break. We can have a computation in the class itself.
Exactly. After 5 minutes we can have.
हाँ, मैं देखा नहीं, ठीक है, आज 2 घंटा का क्लास, तो हाँ, let's today let us compute in the class itself. All of
Okay.
you get ready after the break. Get your pen and paper or tablet if you have a stylus stick. You write it. So let us compute the things in the class.
Yeah. that
Actually,
will be
मैं
fine.
इसके लिए prepare हुआ था, आज जो competition वो p² p³ वो compute
हाँ
करेंगे.
सर. हाँ ठीक है, अच्छा रहेगा.
हाँ,
ठीक.
thank you.
That will be fine. Okay.
So let us take a break. Or any other questions you have in the theory?
I think there is no question, sir. So we can take break.
Okay. So all is clear. The transient, recurrent, everything is. Hope the participants are clear with the concepts. Good.
Yes, sir.
Good. So we'll see after 10 minutes. So let me go to share the screen. I'll give you a numerical example and let us compute all together. Okay. I'll give you an example. Let question number 1. Let say P equal to a transient matrix with the 3 states. Let me have 4 states. Say 1, 2, 3, 4. Okay, we'll do first 3 states, then we can go to make it complicated with go to for 4 states. Yes. Say the transient probability values are as follows. Say 1 to 1 is 0. And say 2 to 1 to 2 is also 0. So this is half. Or let me make it 1. Instead of half, let me make it a 1. 1. And say second also say 0, 0, 1. So this is half. Half. 0. Just a minute, don't start. Let me. So 0, 0, 1. 0, 0, 1. Half. Yeah. Fine. So this is stochastic matrix. So all of you first draw the first draw this, the transition graph. Please draw transition graph. Transition graph means you write down the 1, 2, 3 states and then draw the directed graph. Which state the transitions happen, you draw that. As I also draw after some time, first you all finish drawing. Sorry. Question number 1. Draw directed transition graph.
Done, sir.
Done? Okay, good. Very good.
Participant, you can on your camera, so it will be more interactive also. And we can also take a photo. Yes, participant, please.
Okay, so I hope all of you drawn the. So that is 1, 2, 3. One to three, 2 to 3, 3 to 1, 3 to 2. Okay. Now, construct a second part of the question. Construct a closed subset of yes. So this is A. Already you are done. B. Now construct the closed subset of yes for your S equal to 1, 2, 3. Construct a closed subset of yes. So in this case, the answer is closed subset of S do not exist. Okay, because yes, there is, you cannot make any smaller because each state is communicating with each other state. 1 to 3, 1 to 3, 3 to 2, 2 to 3, 3 to 1, and similarly each state is communicating. This is a continuously, the transitions keep on happening infinitely many times. 1, 2, 3, each state is a class. It itself a class. S itself is a closed. So there is no further reduction can be done. S is irreducible. So there is no closed set exists. That's the reason I asked. S is irreducible. That's the answer. Okay, please verify all of you. I'll just hold for a minute here.
So subset should be proper only.
Yeah, closed subset means it's a proper only.
Okay.
Or S itself is closed. That means you cannot have a, that's what I wrote a closed subset of S here. Or S itself is closed. That's what I meant by.
Yes.
You
Yes.
cannot make
Right.
another subset of S.
Okay, sir.
So S is irreducible. That there you cannot find another subset of S which is closed. Find periodicity. I mean, those who are doing the verifying still irreducible, no hurry. You please do yourself. I don't want to take up your time. So please verify because there is nothing like slow or fast. First time those are doing, please verify yourself thoroughly. Thoroughness is important, not hurriedness. Periodicity. Find the periodicity. So you compute p square, p cube, and so on, and p4 maybe, and then you get a pattern.
Sir, P cube is equal to P.
Good. And then p square equal to p power 4. So what is the period? Period of.
P square is equal to P4 and P cube is equal to P.
So what is the period then?
What, sir?
Period. What is the period then? Periodicity.
2, sir. 2.
Very good. Very good. Good answer. So periodicity is 2. Please verify everyone. I'm waiting. Everyone, just check yourself that you get the answer there.
Yes, sir.
So I hope everyone has done this completed. Or if someone is doing, feel free to tell me. Otherwise, we'll move to the next question. Yeah, I can wait also. Not a problem. We have time. We have. We can. I can wait for a minute or two. Someone is doing. Not a problem. And everyone has to do for some day. First time.
Participant, please on your camera.
On your camera also. Professor Rao, you can on your camera, please.
Okay.
All the participants are requested to on your camera so that we can also have a pick session. We need to have a pick for the session. It is humbly requested to all the participants kindly on your camera. Dipankar, Anshul, Naresh Kamraji, Rekha, Manju Tong. If possible, kindly Anju, Naresh, Dipankar, just for a few seconds. Mr. Hitesh, kindly have a pick. I hope the other will also join now. Vikas, okay, it is there. Both the Vikas are there. Reena, Dipshi, Manju. All the smiling faces. Okay, done. Thank you. Thank you all.
Thank you. Thank you, Professor. Yeah. So let us go to the next question. That is next tutorial question 2. Sorry, some question? Anyone asking anything? Okay. Let me share the screen again. I'll write the second question, second tutorial question. Let xn, let xn be a random variable. Sorry, xn be a random, not random, I'm sorry, random walk.
Screen is not visible, sir.
Oh, screen not visible?
Now it's
Thank
visible.
you.
Thank you,
Thank
sir.
you. Thank you. Let xn be a random walk on Z plus union Z plus union singleton 0. Let xn be a random walk on Z plus union 0. Let pij, p suffix ij, be the transition probability. तो मैं जब लिख रहा हूँ आप ही लिखो अपना पेपर में. Transition probability probabilities. Be the fine. Let Pij be the transition probability from I to j. I to j for all I comma j, this is for all symbol, I comma j belongs to S. So what is our S here? S is equal to Z plus union O. I mean Z plus union 0. O means 0. Be the probability I to j defined by, comma, defined Pij defined as follows. Defined by Pij equal to probability xn plus 1 equal to j given xn equal to I, which is defined as, say this is equal to alpha if j equal to I plus 1, this is equal to beta if j equal to I minus 1 equal to 0 if j not equal to I plus 1 comma or I minus 1. That's how Pij is defined. For all I comma j, that means for all I comma, this is for all I comma j belongs to S. But this is good dot. Suppose, further information given, suppose P00 equal to 1 and Pnn equal to 1. Yeah, and n equal to 1. And then here that means we consider only on the finite state space. That means your S equal to 0, 1, dot, 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 n. Okay. Now, given information, you can find out, draw the directed graph. Draw directed graph and find the communicating classes. Find the communicating classes. Communicating classes. B. Which states are recurrent? Or find recurrent and transient classes. Communicating classes and then find recurrent and transient classes. Yes. So these two, the draw directed. Sorry, I'm writing with my mouse. That's why handwriting. But then hope you understand. I'm reading the question. Let xn be a random walk on Z plus union 0. Let Pij be the transition probability from I to j for all I comma j belongs to S defined by Pij. So and so Pij equal to alpha if j equal to I plus 1, beta if j equal to I minus 1, and 0 if j not equal to either I plus 1 or I minus 1. Suppose P00 equal to 1, this is equal to my equal to P00 equal to 1, Pn equal to 1. Draw the directed graph, draw the directed graph and find the communicating classes. Find recurrent and transient classes, B. And here instead of the Z plus, all the Z plus is although union of Z plus union 0, I consider only finite. Please consider only finite up to n, some state n, capital N. Okay, some integer capital N. Yeah, please try to do with pen and paper.
Sir, I want to ask one thing. Excuse me, sir.
Sorry, did anyone? I was not at the desk here. Just went for a. Oh. So is it okay? Everything, the question is clear? Everyone is working on the directed graph and the communicating classes?
Sir, I want to ask one thing.
Yes, please.
Sir, if P00 is 1, then the probability to go from 0 to any other state must be 0.
Correct.
Correct? So,
Correct.
Pij is alpha if j is I plus 1. It doesn't hold if I is 0.
Correct.
So, shouldn't we write here except I is equal to 0?
Correct. That's what the last condition says, 0. Only one, this condition, and then P00 is given on top of that. See here, j not equal to I plus 1, not equal to I minus 1. Last condition, and then P00 equal to 1.
No.
So if we given conditions, the first row is 1 alpha 0 0 0. So
Yeah.
Correct. That's what that means. That's why the suppose P001 means from 0 to other states not happening. Transition.
go to the Pij as we defined Pij. If I is 0 and j is 1, then its probability is alpha.
Yes.
No, it can't be alpha. In that case, alpha is 0 now.
For higher states, for alpha, if j equal to I plus means moving higher states, j equal to I plus 1, alpha. Lower states, I minus 1, the previous state, I mean, I minus 1, it is beta. When j not equal to I plus 1 or I minus 1, that means the transition is not immediate to the next ones, then it is if either I plus 1 or I minus 1, then it is 0. That means other transitions are not allowed. Only next higher state or next lower state, I to j.
Sir, actually, they wanted to say that you must find the definition of Pij like I is different from 0.
Yes,
Correct.
of course, I want to say that, sir. We should put some other condition that here j I must not be equal to 0. Otherwise, the definition is incomplete.
Oh, you meant to say that, okay, that means this given, this is enough. P001 means absorbing state.
Okay.
Okay. This means suppose P00, this is also part of the given information. Yeah, definition. No, this is given information. Yeah, definition of, I mean, given hypothesis. This is also given information P00 equal to 1. That means 0 to other states transition not happening from this. Any I comma j which is not equal to 0. Any I comma j that is not equal to 0. This is for any I comma j which is not equal to n.
Yes, sir.
It means first row should be 1 0 0 0 and so on. Last element is also 0, and last row must be 0 0 0 0 and last element is 1.
Very good.
Second
And the
row
second
is
row?
beta 0 alpha and all other elements are 0.
Very good.
Third row is 0 beta 0 alpha, all other elements are 0.
Very good. Oh yeah. Yeah, please. I'm waiting. That's the thing. I'm still waiting here. Not a problem.
So here we have 3 classes then, sir.
क्या classes?
0 only, 1 only, and the remaining all.
0 only and 1 only?
Separate classes.
0 and 1?
No, 0, singleton, single 0 state.
हाँ, single 0 और क्या?
Single 1 state and the remaining states separate.
Single n.
So total 2
No,
states.
it's
Single 1
not
क्यों आ रहा है? Single 1 क्यों आ रहा है?
One is also absorbing now. One is also absorbing state.
No, what
One
is
is
no? What is
N,
no?
N, sorry, N.
हाँ, correct.
0.
Single 0, single n, and remaining all states are
Yes.
3 communicating classes. Very good. Everyone agree with that?
Yes.
Yes, sir.
Very good. Very good.
So absorbing states are recurrent and the remaining are transient.
Fantastic. But please, everyone, that's good. Very good answer. And I appreciate that. So absorbing states 0, n are the recurring. They are the only 2 recurrent states. Rest all are transient states.
Yes, sir.
Sir, should not we say that it will depend on alpha and beta? That means if alpha is equal to 1 or beta is equal to 1.
Both
That's a good question.
One, their sum must be 1. So if
Yeah,
they are
here-
non-zero, then this is the answer.
Because alpha for j equal to 1 means j plus 1 means every state that is moving. You see, for all j, you are right. I mean, if j is not I plus 1 for each j, alpha could be 1. But here in the definition we read j equal to I plus 1. That means each j, when it is moving for higher state, is alpha. That means there is a chance of moving to the higher state.
So can you please repeat? I didn't get your point.
Because we wrote alpha, if j equal to I plus 1, that means whenever transition happening for higher state is alpha.
But
Okay,
alpha
that
could be
means
1, but alpha could be 1 and beta is 0. That is also the possibility. Sir.
Yes, when alpha is 1, what is happening? It will stop
Stop at
for
N.
higher state. Yes, by the next state. Going to the next state is fine.
Yes.
Going next to the higher state is fine, not a problem. Similarly, coming down to the lower state also fine. Coming to the lower state also.
Can we say alpha plus beta is 1 if it is a stochastic matrix?
Correct. If alpha plus beta equal to 1, then it's a stochastic matrix.
But it is always restricted or not?
Yes, it has to be. It has to be because a random walk I wrote in the Xn is a random walk. Alpha plus beta equal to 1.
Sir,
That's a good observation.
sir, when alpha plus beta is equal to 1, then last but 1, and n minus 1th row, elements are 0, 0, 0, 0, alpha. Then
Yes.
how can be it stochastic matrix?
Exactly.
Second last row must be 0, 0, 0, beta 0 alpha.
What will happen to the n minus 1th row? Anyone
Last
can?
entry will be alpha.
Yes, anyone can tell what will happen to the n minus 1th row?
0, 0, 0, 0, alpha.
N, or it can move to state n minus 2.
Yes. Correct. That's why this particular question will actually expand all the things so far you learned in the today's lecture and yesterday's lecture. All things are coming up back and back again. So what are the recurrent classes here?
0, singleton 0, and singleton n.
Singleton 0 and singleton
N.
n. Very good. Singleton 0, singleton n. Can we have any closed set? I didn't ask that, but can we have any closed set here?
Sir, is closed set and communicating class both are the same thing?
Need not be. All communicating classes need not be closed. We saw already in the example.
Okay, sir. Okay.
All the communicating class, earlier example also we saw today.
Only
Sorry,
singleton 0 and singleton n are closed.
Very good. Singleton n, singleton 0 are the closed sets. So the other question, as sir one was asking, in the previous example, we saw one of the example there. Their communication is happening, but they are not. That is not. See here, the communication between. This is not right example. Another example. Let me take it. Yeah. Here see 1, 2, 3. They are communicating to each other. Transition 1 to 2, 2 to 3, 3 to 1 is a communication happening, but 1 to 3 is not closed. So communication class, this is a good question someone asked. So all the communication classes are closed? Need not be. 1, 2, 3 is communicating with each other, but that is not closed. Because here 5, 6 are closed. 5 and 6 are closed. So all the communication classes need not be closed. Is it clear?
Yes, sir. Clear, sir. Now it's clear, sir.
That line one can write down in the somewhere in the this thing. All the communication classes need not be closed. I'll wait for a minute and then all of you finish. We'll go to the one more. और एक इसके लिए टाइम है ना प्रोफेसर कुमार जी?
Wind up right now.
We can wind up. Okay.
Okay. It will take 2 to 3 minutes more, and then you can over it.
Okay.
It is already late, and you see, I think participants are doing well, and
Yes.
they have taken an interest. I can see, and they are attempting the question also. So that's quite good. I'm happy that the participants are quite serious.
Yes.
About all this, and they are taking interest. That is the purpose of this program, and I thank for all this seriousness to the participants specifically, because that is the purpose of this course, that they go through the specific topics, learning and training on that is on stochastic processes. And I hope that you see in any program, if 50% at least are successful to attempt all the things, that means it is a grand success. So anyways, I hope this is going wonderfully. Not 50%, more than 80% are doing wonderful. So thanks to the participants for interacting with our expert, taking seriousness in all these sessions, and also patiently listening to all the lectures. And of course, even sometime goes beyond the scheduled. You bear with us. Thanks a lot, especially to the participant. And there are no words to thanks Professor Rao. He's humbly taking too much time, giving so much time to all of us, sitting there and right time to you see so bumper to bumper lectures are going on, and he's continuously taking up all the sessions. So thanks, Professor Rao. We are really obliged that you are doing wonderful and for all these things. From our behalf, myself and the department and Maharshi Dayamshi Rohtak, we wish happy Holika Dahan and Holi to all of you. And since today is the spiritual day of the Holi and being celebrated all around, and even on our campus, our teacher club has organized a dinner for all the faculty members and their family, and we are missing that also. My family and all, we are here, and we have to rush to there at the end only, because the program was started at 6 p.m. and now it is already almost over. But anyways, it is a nice time with you, sir, and the participants, and thank you very much on this auspicious day that we are here, and we are learning and getting a training. So that is a very important point. Thanks a lot, and I wish happy Holi.
Happy Holi to all.
All of you have a colorful days ahead with all your family members, and you enjoy your life with all colorful things. That is my wishes. And in the morning, you enjoy gulal, you enjoy flower, Holi, and have sweets at your home. And in the evening, we again met for the last session of last day and sessions of this course. And of course, at the end, we'll be having a valedictory ceremony, and eminent personalities are joining with us in that valedictory. So thank you very much for being on the board, sparing your valuable time. Thanks a lot, and happy Holi once again.
Yeah.
Happy Holi, everyone. Thank you, sir.
Thank you so much.
Thank
Thanks
you.
a lot.
Thank you, sir. Namaste, Professor.
Happy Holi. Yes, good night to all of you.
Yes, sir. Good night and happy Holi.
Good night.
Happy
And
Holi to
you
you
have a
too,
good day,
sir.
sir.
Yeah, thank you.
You might be enjoying Holi today.
No, tomorrow. Tomorrow we have a Holika
Tomorrow
Dahan.
is
Tomorrow
fun.
evening.
Yes.
Tomorrow, yeah, it will be
Tomorrow,
tomorrow.
Friday, they kept a Holika Dahan. And then
Yeah.
Saturday morning, Holi, actual colorful Holi.
Okay, so you play there?
Yes,
Have
yes. Okay.
colorful days, huh? Right.
Yeah, already yesterday I purchased certain Holi, the historic guns, all these
Items.
kids.
For your kids.
Yes, for my kids. Yeah.
Sure.
Yeah,
So
we'll have fun.
nice. You see, this program is scheduled in such a manner that we have started from a Pi Day, and we are ending with the holiday.
Correct.
The celebration
Yes.
festival day. So
Very
this
nicely.
is say all going well. I started with very mathematics pi and ending with the all jubilations, colorful days.
Correct. I agree with you. And you all also have a nice dinner in the campus.
Yeah,
Enjoy
sure.
it.
Thank you. Thank you, sir.
Thank you. You enjoy and have a
Good night
rest.
to all.
And
Good
all
night, sir.
participants, enjoy your dinners. If you have been here, we can serve you a very special dinner here. But sorry, this is online. And thanks a lot.
Thank you.
Yes, sir.
See you, everyone.
See you tomorrow. Yeah.
Yes, sir.
Bye.